Alright folks, I'd like to explain the concept of interference. This is an important concept because your examiner particularly likes to test this for structured questions, so paper 2, paper 3. And at the same time, it is an important concept because it forms the foundation later on for two-source interference, Young's double slit, even single slit diffraction. Okay, so the main thing you need to understand, right, when do you get constructive interference, destructive interference, right? What are the properties of constructive and destructive interference, and what we call interference pattern. So is that a repeating pattern of constructive and destructive interference occurring through time or through space? Okay, so let's look at the formation first. So in order to understand whether constructive or destructive interference happens, right, we need to know whether the waves are arriving in phase. So what that means is the crest and the crest arrive at the same time, or are they arriving pi out of phase? Because if they're arriving pi out of phase, then the crest and the trough arrive at the same time at the same particular location, right? And since we have to do a vector sum of the displacement, the wave will essentially destroy each other or cancel out. Okay, now how do we know then the constructive or destructive interference takes place? You will have to find three different factors. Okay, the phase difference due to the source, phase difference due to the path, and phase difference due to any other effects. So because they are all scalar quantities, so the total phase difference, right, is the numerical sum of the three. So let me use an example to show you what I mean. Okay, say we have got two speakers S1 and S2, they are separated by 3 meters as shown below. They play two identical notes of wavelength 2 meters. So it's at this point now an important information is given. Since they are identical, the phase difference due to the source is 0. Okay, what that means is when S1 produces a crest, S2 will also produce a crest at the same time. Let me use a different color. Okay, in contrast, if the phase difference due to the source is pi, then what that means is when S1 produces a crest, S2 will produce a trough. Okay, for this question, they are in phase. Okay, so I'll just remove this. Okay, let's look at what else is given to us. We are also told, right, okay, that there is a receiver placed at position P1, P2, and P3. Alright, and P1 is equidistant from both speakers. Now this is important information. So if P1 is equidistant from both speakers, then we will say that the path difference, which is the numerical difference between these two distances, is actually 0. Okay, there is a formula for finding the phase difference due to path, right? And so it goes by delta x over lambda times 2 pi. Now because delta x is 0, phase difference due to path is 0. Right, and phase difference due to the source is 0, due to path is 0. Okay, and so the total phase difference is 0, and we will say that the waves arrive in phase, constructive interference takes place. Now we can visualize this actually. So see, because the wave from S1 is traveling at a particular speed towards P1. Similarly, for S2, it is also traveling at the same speed, right? Because it's the same wave. Okay, so traveling at the same speed towards P1. And because the distance are the same, we will expect that these two waves must arrive at the same time. And so since they're arriving at the same time, then the two crests will coincide, troughs will coincide. So at P1, crest will arrive with crest. Okay, now but we now have to put all this into words. Okay, so like I said earlier, it's very common in structured question. Alright, so I'll point out path difference since that's what we are trying to find. Phase difference due to the source is 0. Right, and critically the wave will arrive in phase. Right, this must always be mentioned before you say a constructive interference occur. Okay, arrive in phase, therefore constructive interference occur. Okay, now let's look at P2. Let me erase first so that it's less cluttered. Okay, let's look at P2. Okay, so P2, it's further from S2 than it is from S1. Right, so if I use Pythagoras theorem to find the distance S2, P2, that will be 5 meters, which means the path difference at P2, just write 2, okay, is going to be 5 meters minus 4 meters for S1 to P2, right? So 5 meters minus 4 meters. So that's going to give us a path difference of 1 meter. Okay, right. How can we visualize this? You see, so when the wave comes out from S1, so similarly as before, this wave, right, okay, is going to be traveling towards P2. They travel. The wave from S2, same thing, it travels. But because of the difference in their path, right, the path difference, the wave from S1 will reach first. The wave from S2 will reach will travel a distance of 4 meters. So currently it is 1 meter behind S1. Right, so if we play this out, so as the wave from S1 continues, the wave from S2 continues as well. See, right, you can now predict what's going to happen. So the wave from S1 has undergone half a cycle. The wave from S2, the crest, is just reaching, and you see now we can see that the crest and the trough are going to arrive at the same time. So that's a pi hour phase. Okay, see, so in formula, when we calculate, we will see that as well. Phase difference due to the path, delta x, right, over lambda, times 2 pi. So then that will be 1 over 2 meters times 2 pi. This is pi hour phase arrival. Okay, so same thing for, the explanation, right? We're going to talk about the path difference, which is half a wavelength, right? The sources are in phase, so they will now arrive completely out of phase. Okay, destructive interference occurs. Okay, right, just one more very quickly, just to, show a bit of variation. Your examiner, right, may not be so nice as to give you like, wow, so many points to find. So maybe they'll just give you, 1 point that is much further away. So let's say P3, right? So you will now have to find S1 P3, S2 P3. As I'm going through, you should, now try and think through the step and preempt what will my next step be. Okay, so I'm going to use geometry, right, to solve for the distance of S1 P3. Okay, so this distance will work out to be 4.572 meters. Okay, similarly, I'll use geometry to solve S2 P3. So that is 6.572 meters. The path difference, at P3, right, which is the difference between these two values, works out to be 2 meters. Okay, and so if I calculate phase difference due to the path, then that will be delta x over lambda times 2 pi, which is 2 meters over the wavelength of 2 meters, so that's 1 times 2 pi, so it's a phase difference of 2 pi, right? And then you plus a phase difference of 0. Okay, now phase difference of 2 pi, which is an even multiple of pi, right, is also considered in phase. Right, why is that the case? So when the wave from S1 is traveling towards P3, now the wave from S2 does the same thing. Right, let's give it a while. Okay. Okay, so the wave 2 is also doing the same thing. It is traveling towards P3. Now as the wave of S1 is traveling, see, S2 is always lagging behind, and by the time the wave from S1 has reached P3, S2 will be exactly 2 meters away. Right, that's the path difference that we found earlier. And 2 meters corresponds to 1 wavelength. So I'm trying to, show that the crest from S2 will eventually coincide with the trough. Sorry, the crest from S1. Right, so the 2 crests will arrive at the same time. Okay, so this wave travels in, followed by its next cycle, and the wave from S2 would have traveled here. Okay, and this is why whenever it's an even multiple, of phase difference, we will also say that eventually the wave will arrive in phase. Okay, so that's for the formation. Okay, the next thing that you will need to be able to work out, right, it's the well, okay, it is the properties of the resultant wave, okay, that is formed at P1, P2, P3. What do I mean by that? Okay, now in order to understand what I mean by the properties of the resultant wave, okay, so we have to first recap a bit of concepts in terms of amplitude, okay, as well as intensity. So amplitude we know is actually the maximum displacement. Right, so this distance over here is the amplitude. Okay, intensity on the other hand is a measure of the energy, right? Okay, that reaches a particular point due to the energy propagation. Okay, and so in waves there is a relationship between intensity and amplitude. So intensity is proportional to amplitude squared. Okay, the fundamental reason for that is because for intensity it is power over area, right? But since power is proportional to energy of the wave, and energy of a wave, right, is proportional to amplitude squared. Okay, so when we link them up together, then we can also conclude that the intensity is proportional to amplitude squared. Okay, now so supposing, right, we have now a wave traveling from S1 that has an amplitude of A. Okay, and correspond to A, it is an intensity of I. Now, the wave from S2, since the question tells us it is identical, right, so we'll also have an amplitude of A as well, intensity of I, right? But see, when these two waves travels towards P1 and eventually they reach P1, right, what we know is that constructive interference will take place, right? And in constructive interference, the crest and the crest will construct, right? So you can think of it as adding up. And so you're gonna get a waveform at P1, right, that has twice, okay, the amplitude. So since it has twice the amplitude, right, then intensity is proportional to amplitude squared. It actually gives us an intensity of 4i. Okay. Right, so it's not intensity of 2i. Please remember this. It is always the amplitude or the displacement that you do a vector sum of. You never do a scalar sum of the energy or the intensity. Okay, now some students might ask then, but there is also this law called the conservation of energy, right? So if now I have an intensity of I, another intensity of I from each of the speaker, right, and they travel towards P1, and suddenly I get 4i, then wouldn't we have just created energy out of nowhere? Well, the reason why energy is still conserved is because we cannot forget that there's also destructive interference, right? So at P2, this was a point of destructive interference. At destructive interference, right, the amplitude will have cancelled out, okay, because it's identical, right? So A cancel out A, and you'll get a resultant amplitude of 0 and an intensity of 0 as well. See, so sort of like at P2 we have like taken away energy, but it's not. It's just that the energy have redistribute itself, right, over this region over here. Okay, right, so if this is 4i, this is 0, and let's say at P3 the wave that arrived is also A, and therefore at P3 it is also 4i, on average it is still 2i. Okay, energy conservation is, to me, one of the grand laws of the universe that one will never be violated. Okay, right, so that's the second type of question that you must be familiar with, dealing with the properties of the resultant wave in terms of amplitude and intensity. Okay, simple rule here is just remember, never add up the intensities. Okay, now the third kind of question for interference. I call this third kind, right? Okay, finding a pattern or interference pattern. Okay, so the question might go something like this. Suppose they now give you some random point, right? Okay, so let's say here. Okay, so this point, right, it's, you know, again, some distance from S1 and some distance from S2. Right, so maybe I call this now P4 lah. Okay, right, and maybe they'll give you, you know, the distances and so on. So you can again use geometry to find the path difference, right, of S1 to P4, S2 to P4. Okay, now, and so let's say this path difference that I have, you know, found is let me just think of a random number. Okay, let's say 6 meters. Right, so 6 meters. If I were to now find the phase difference due to path, delta x over lambda times 2 pi, right, so that's going to give me 6 pi. Okay, so we now know this is a constructive interference since it's an even multiple of pi. Okay, now, so the examiner may ask something like this, you know, so between P1 and P4, right, so P1 is recall, is the equidistance point. Between P1 and P4, how many minimas, right, are there? Okay, how many minimas are there? You know, so what we can then do is identify a pattern. You see, so just now at P1, this was a constructive interference where the phase difference was 0. P2, it was a destructive, phase difference was pi. P3, it was a constructive again, right, phase difference of 2 pi. And so then this pattern is going to repeat, right, all the way to P4. And so in between, whenever there is an odd multiple of pi, there must be a destructive interference. So from 0 to 6 pi, right, you are going to see a, you know, minima or destructive interference whenever there is pi. Somewhere between P3 and P4, there will be a 3 pi. Okay, 4 pi is not counted. 4 pi is a constructive interference, and a 5 pi, right? And then P4 you reach 6 pi, right? So what that means is between P1 and P4, we can now conclude, right, that there is pi, 3 pi, 5 pi, that there will be 3 minimas that is observed. Okay, so those are the, you know, 3 question types that you must be familiar whenever we are dealing with interference type question.